Tom Field of Field Tested Systems is an amateur astronomer who wanted to do a little bit more with the stars. He's got a spectroscopy product called RSpec that I happen to be a licensed user of. I've met him through many a conference, taken workshops with him, and since this pandemic, he has been visiting many astronomy clubs across the country, and I have seen and heard his presentation, count them, 6 times.
Oh my God. You need some coffee, my friend, before I go in. Good.
I am equipped. He has not bored me once. He's a very animated presenter, and I'm going to let the rest of the bio go for him. You guys all know the PDF he sent out. Send it to you. He's a very fine speaker. He's got a very fine product and a fine gentleman. Tom, please welcome to the Astronomical Society of Greater Hartford.
Thanks so much. In fact, before the meeting, before some of you were in here, I was mentioning that I rode my bike from Boston to Philadelphia when I was a third my age in 1972, and came down the coast and landed at Gillette Castle, and they had this little like 4-car ferry that went across the river there. That's the last time I was in Connecticut, I think.
There you go.
So John, you can see that prism there. Thanks for that
indeed.
introduction. Sorry for a little bit of stumbling. I like your logo. Looks like maybe a Celestron telescope there. Not sure. SCT.
It is.
Good. So how have we managed to discover so much when we really haven't even left home? How do we know so much about the stars? Of course, imaging we've been doing for more than a century and a half or a little more. And if you wait a while, you can see a 2-dimensional view where you actually 3-dimensional. I'm just setting some things up on my screen here where you can, there we go, where you can get a sense of depth and that things are further or closer to us than others. If you wait a while, the time dimension comes in and you can see things actually change. Up in the upper right-hand corner, for example, you can see a couple stars that are going on and off, so to speak. And if you spread the colors out, and by the way, this rainbow is from not far from you. It was taken at Lake George. One of my family members live up there. It was taken in March or April. You get this beautiful dimensional view with a lot of information. Those gaps are part of what we'll be discussing tonight. I love the colors. And these gaps are like a barcode for our star and for other stars, and can reveal things about the composition. And I'm not going to read those bullets, but I'm going to show you some examples tonight of the kinds of things we can do. A little bit of history here just to get started, just so everybody's on the same level. You can see that Sir Isaac Newton, as most of us know, discovered that you can split light through a prism and go from white light to its component colors. You can also bounce light off a finely lined surface like that DVD, or even through a finely lined piece of glass called a diffraction grating. Bunsen invented his Bunsen burner, you can see down here, to burn a sample and then put the light through a prism and look at the result. He was a real pyromaniac. He burned everything he could find. And the cool thing is he kept notes, really good records about what he observed. And so those notes really serve us even today, as we'll see in the next 20 minutes or so. Kirchhoff, this guy over here, we won't talk much about him. He was a contemporary of Bunsen's. Oh, one thing about Bunsen before I leave, he never patented, he deliberately didn't patent his Bunsen burner. He said, I want this available for the benefit of humanity. Of course, today there'd be 6 patents on every screw and bolt probably. So this guy Kirchhoff, I don't want to spend a lot of time on him, just one little piece of this slide here. And that is to look, there's 2 different types of spectra. One has a rainbow behind it in rainbow order, Roy G. Biv order, with gaps. And the other you can see down here, those are, it's a dark background, but it's got some lines. Now, what's interesting is regardless of which one you're getting, the lines, whether they're gaps or whether they're emission lines, are in the same position. And which you get depends on temperatures of the gas that the light's going through. That's what Kirchhoff talked about. We're not going to get into those details tonight. So, but these lines are like chemical fingerprints. And you can see, for example, in hydrogen, if you burn hydrogen gas and look at it through a prism, you see that line right there. But it doesn't exist if you got some helium like at a florist, to blow up a balloon. you just wouldn't see that line if you were to look at the spectrum. Let me come down here and ask PowerPoint to keep my cursor visible. Hydrogen's so common and we use it so frequently. It's nice to know this name to refer to the collection of lines, hydrogen bomber lines or bomber series. And we've even given them Greek names, scientists have, to talk about them, much like we give Greek names to the stars in intensity order in the constellation. So this red one is hydrogen alpha, and this one in, I guess that's robin egg blue, that's beta. And we're going to see these as we talk about it tonight. We're not going to get too deeply into the science. In fact, I used to, and John, you may recall in some of my recent talks that I had this list of bullet points of things that I wanted to communicate, and I showed them up front because I was thinking, why not just show people what I'm trying to talk about and what the key points I think are that will be most valuable to them. But it was a slide with so many bullets that nobody wanted to read, including me. So I gave that up. But I've got this new approach, and that is I've got this little thing, and that will be an indication that I'm about to say something that used to be on that slide that I think is important. And this is one of those, this is new to me, so bear with me. This is one of those points, and that is, I think all of us falsely concluded that we needed to be astrophysicists to do astronomy and especially to do spectroscopy. And I want to, again, destroy that myth tonight. I'm going to talk about a lot of stuff, but I'm not going to go very deep because, well, I'm like a river, really broad and not very deep. And that's the great thing about doing spectroscopy as a hobby as opposed to professionally or as a student, is we only have to learn as much as we care to. So I won't get into a lot of the details, mainly because I don't know them, you know, the background of how some of the examples that we look at work. So this is a periodic table I created a few years ago. We sell it mostly to schools and amateurs who are really into spectroscopy. What I wanted to show you here is there's hydrogen alpha, there's that robin egg blue hydrogen beta line. And notice that if I bring up helium here, very different lines. That's the fingerprint that we're talking about. So fortunately, we don't have to burn things anymore. In fact, I created this camera for educators to look at gas tubes. And this is something new for me too. What I'm going to do, did your screen change, John, to the software screen?
No, well, the software is still showing in this. Yes, it is our Spec Explorer.
So is it?
But I can't tell if it's.
That well, can you see me waving my hand in front of a camera here? No. Okay.
No.
Somehow. So.
No. Yep. That just changed it, but it went back.
Oh, so you can see me with my hand in front of the camera?
No, it did, but it maybe do it again.
I'm doing it now.
No, sorry.
That's weird. I think you may have set up so I can only share apps instead of screens. So let me come back. I apologize for this technical glitch. Let me stop sharing my screen for a moment and
allow some multi-pin.
Let's see. It says select a window or application, but it's not showing me any windows.
I wonder what multi-pin is. Whatever that is, I just allowed it.
I don't think that's for us. But anyway, I'll just switch apps here and show you that. That's what I wanted to show you. You can see my hand now, right?
Yes.
Okay. So all I wanted to show you for all that suffering is here's a gas tube. It's filled with hydrogen. It's even labeled hydrogen there. And if I put this in the power supply and turn the switch on, there you can see the spectrum. And that's our hydrogen alpha. There's the robin egg blue beta and gamma and so forth. So this is what, well, for educators like this, but what I wanted to show you was this is exactly what Bunsen saw when he burned hydrogen. And we're going to look at stars that have the same lines. And that's how we learned a lot about what the stars were made of. Well, that was pretty painful to get to. Let's just go back to sharing my PowerPoint screen again. And that would be this screen. There we go. So far, everybody I've talked about have been old white men. I'd like to just share some of the non-old, non-white, non-men in the field. One is Annie Jump Cannon and her team of computers. They were prohibited more than 100 years ago. Let me turn that lamp off. From getting access to the Harvard telescopes because of their gender. So what they ended up doing was studying the glass photographic plates of spectra. And first of all, they were incredibly fast at it. They classified hundreds of thousands of stars and photographic plates. But more importantly, because they had so much data and because of their deep understanding of the field, they were able to come up with a category system that actually worked as opposed to all the ones that had come before. Priyamvada Nataraja, she's at Dartmouth. She studies gravitational lensing and massive black holes. Nancy Grace Roman was the first astronomer at NASA. She got her PhD in the late 1940s and was a big proponent of the Hubble Space Telescope and helped make that happen. Elisa Quintana studies exoplanets on red giants. And finally, Jedediah Eisler studies hyperactive black holes at Dartmouth. So this, again, this is a fun slide for me to put together this summer because there's so many women out there who have done amazing things in the field that I didn't know about. We've come a little ways, we have a long ways to go in terms of equality in our field. What I hope to talk about and educate you on tonight is this star analyzer grating. It's just an 1.25 inch grating that screws onto your camera. So this is a ding moment because I think a lot of people think that it's expensive to do spectroscopy. This is just about $200, so it's not really hard. It's not expensive, nor is it hard. That's what I wanted to show you on this screen. There's a little adapter here screwed onto a DSLR so you can mount the grating right on a DSLR standalone, or you can put it on almost any camera, whether it's a FITS camera, cooled, uncooled. On the lower right there, it's just a ZWO camera. It can be color, can be mono, doesn't matter, or even inside a filter wheel. So the ding moment for this is you don't have to be a do-it-yourself or an equipment person, because I'm certainly not. It's just like a standard filter cell that you'd use on almost any camera. You can even piggyback a DSLR on your telescope so you can multitask and do some regular imaging as well as spectroscopy at the same time. Okay, so we got all that background out of the way. Let's look what we can actually do. So we've got a star, we've got a grating here. The starlight goes through it, and some of the light, not all of it, some just continues on down to our sensor as a star image, and some of it gets split into the rainbow, just like Newton split light with a prism. There's our spectrum. And let's look at this great example. These are different spectra captured by Torsten Hansen with an 8-inch Newtonian and an imaging source video camera, much like the ZWO cameras. So this is a ding moment because I think people think, oh, geez, I'm going to have to be an expert imager to capture spectra. And in fact, that's not the case. I mean, short exposures, right? With a video camera, we're talking sub-second exposures. Sure, you can go for dark sky sites, bigger telescopes and so forth, but it's not necessary to do a lot of really interesting stuff. So each of these spectra are of different star, and you can see here, they're actually in temperature order, starting at the hot and going down to the cool type M stars. I'm not real fond of the "Oh, be a fine girl, kiss me," or "guy, kiss me." In the Me Too era, I'm not sure that's politically correct. So I found another one online. It's not quite as catchy yet, but it may apply to some of the people in this group though. It says, "Okay, boomer, a fully green kilowatt matters." So maybe we can use that.
What?
But I mentioned in that earlier slide with the bullets that one of the things that we can do with spectroscopy is tell the differences in temperature in stars. Professionals do not use colors because there's a lot of confusion that can occur in colors because there couldn't be, for example, there can be some interstellar gases between us and the star that would redden the star, for example, gases or dust. So somebody's not muted. That may be you, John. Yeah, that's you, John. We can hear your kids in the background. Maybe you can mute yourself.
No, it's my wife in a meeting, but I will fix that.
Great, thanks. So I just want to show two quick examples here.
This says on November 14th.
John, you muted Tom.
I noticed that, but I actually muted myself, but he got muted.
There we go. I'm unmuted. Thank you. Okay. So These bands here on the cooler stars are because the outer shell of these stars is cool enough that some more complex molecules don't get immediately incinerated. In this case, for these type M stars, it's titanium oxide. But I don't know anything more about titanium oxide, but the fact that we see it on cooler stars because it's a complex molecule that can survive. But let's look here at that line. That's in the robin egg blue. That's the hydrogen beta line. Notice it's more pronounced here. So that's how professionals tell star types, because certain stars have certain lines or features and others don't. So this is a type A star, like Vega, for example, and it's got the most prominent line. Why would that be? Why would the lines vary? Just a little bit more science here. And that is, the Bohr model of the atom has numbered shells that electrons are orbiting in. And sometimes they jump between shells. And when they jump between 2 and 4 or 4 or 2, they create a feature right here at 4800 and so. So on these hotter type B stars, not as many electrons end up on shell 4 because they're hot enough that those stars, as the electrons getting pumped up, they just keep going to 5 or beyond. And on these cooler stars that have either dimmer or non-existent lines here, a lot of the electrons don't get pumped up high enough because the star is too cool to get all the way up to 4. They may get to 3, but they don't end up making that transition. So that's why we have different intensities of this robin egg blue hydrogen bomber line. So you see that crosshairs there. Suppose I got time on the Hubble Space Telescope and I did a study and I wrote a paper and I said, yeah, we saw a little bit of dimming down there in the robin egg blue region. Of course, I wouldn't get published, right? And that's because it's not scientific. To be quantitative, we convert this data to an intensity graph. So for example, we have here in this axis is intensity. So the star is really bright. So this peak is very high, but the star is pretty narrow. So this isn't very wide. Over here, well, this area is pretty dim, but then this area is bright and then that area is dim. So this goes from dim, dim, brighter, 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 then dimmer, 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 dimmer. But here's the really cool thing. Look at that dip there. That dip lets us do science. Now we can study the width of that dip, where it's located, how does it look tomorrow night, or how does it look on other equipment or other stars, or all sorts of things. So now we're doing science. By the way, my wife, this screen reminds me, my wife always wants me to dress for success, and I think this is probably the screen to do it on. You can see there's the hydrogen alpha line right there. Somehow I don't think this is what she means when she talks about, in fact, it's not somehow I know, she's told me straight out, that's not what I'm talking about. But, I wanted to mention something for those of you at home, which is all of you. Between you and your wife, I think you're probably going to know exactly what I'm talking about here, your wife or your husband or your spouse. And that is, we're all about colors in spectroscopy. If you look on this hydrogen alpha region, you get down deep and it's starting to, it's not red anymore, it's gray. And my salon's not answering the phone. Another salon I know of, they don't have any appointments available. So, like I said, I think maybe some of you have been down this road too over the last 6 or 10 months. So how do we get this graph? So my story is I got a star analyzer grading. I wanted to do some spectroscopy. I went out one night right outside the window here in my backyard, 3 miles from downtown Seattle and Pike Place Market. Saturday night, in August, I went out. I had a little webcam. I had duct taped it onto the barrel of an eyepiece that I had taken apart. I came in at midnight with some video, and this is a frame from that video, of Vega. I had a sore neck. My knees on my jeans were grass stained because, it's Vega in the middle of the summer. So the next morning, Sunday morning, I tried to create a graph from this. And this literally is a freeze frame from that video. And I failed. And I got so frustrated. I downloaded some freeware that was out there. One of them wouldn't install. 2 others were in French and they kept crashing, and the error messages and half the screens were in French and there was no manual, and they just weren't up to the usability standards that we've all become accustomed to. So like I said, I quit. I gave up. I told my wife, this is supposed to be fun. It's a hobby. This is not my job. And so I put the grading in the drawer, but it kept weighing on me. And a couple weeks later during the week, during a lunch break from work, I thought, you know, this weekend I'm going to write some code. I've been coding since the 70s, or actually 60s, to be frank. And so Saturday I wrote something to create this graph, and this is that graph. And now 10, 15,000 hours later and 10 years later, the software is almost done. My wife keeps saying, would you finish the software so we could start having dinner at the same time and at a decent hour? It's done, really. I'm just kidding. But I think, again, one of the obstacles to learning something new like this is the very realistic conclusion, oh no, I'm going to have to learn another piece of software. So I don't want to spend a lot of time at this because I know it's after dinner there. And if I spend very much time showing you software, I know that you and I will fall asleep. So all we'll be seeing at that point will be the tops of your heads as you nod off. So let me bring up, if I can, my software screen. God, I just don't, oh, there we go. So I'll spend just a couple minutes here, I promise. So let me just do a little arranging here on another monitor. Here's our spectrum. I happen to be using a color camera because it's more intuitive if you haven't seen a spectrum before. Mono's a little more sensitive, a little bit more accurate scientific data. Notice there's a gap there, maybe there's some gaps there, there's the star. So all we have to do to study spectra is bracket in the region we want to study, and now we have the spectrum. In fact, let me just turn that aside. That dip there is that gap. This is intensity scale here. This peak here is the star. So the next thing is, well, big deal. So there's a lot of dips. How do we know what they are? Remember, I mentioned Bunsen created a catalog. Well, the great-grandchild of that catalog, we still use today. So I can come up here and say, show me on the graph where the Balmer lines were that Bunsen found when he burnt hydrogen. And look, we've got a dip right where that line is. We've got one right where that line is. Not all the way across because our camera gets pretty dim here in the ultraviolet. But this is pretty good evidence that we're seeing hydrogen on the star. As the starlight moves or leaves the star, that outer shell is causing these transitions to absorb a little bit of light. That's pretty cool. On a backyard telescope with a video camera. We can fill it in like that to make it a little more pretty. And the cool thing is, I know the club does outreach. I was really happy to hear a little bit about that before the meeting, a lot of outreach apparently. This is the kind of thing, especially for high school kids, but really any audience, that you can augment your current outreach. Because this is also a ding moment, and that is spectroscopy is much more immune to urban light pollution because we're not involved with all the aesthetics and the color balance and getting everything all perfectly and aesthetically pleasing. In fact, we don't do much of that post-processing because we want the photons in our images that we're evaluating to be exactly like they were that they hit our camera. We don't want to mess up our data and cause this dip to be deeper because we boosted this region, for example. So it's the kind of thing you can do in the city. In fact, this is actually a video that I paused for a moment. I'm going to start it playing. And you can see our image there. Our star is changing because of our seeing. And of course, our data is changing because of our seeing. This is a fantastic screen because it's colorful and it's moving. It really captures people's attention. You can use this as a springboard to talk a little bit about the science. You don't have to be, like I said, a PhD in astrophysics to talk well about this kind of thing once you've done a little bit for yourself and really help people understand how it is that we know what the stars are made of. A lot of people, especially in better educated communities, will know, yeah, wasn't that in the 3rd or 4th Cosmos series by Neil deGrasse Tyson and the right? So the only other thing I'd like to show you, and then we'll leave this screen, I'm going to zoom in on this feature here. That's our hydrogen alpha. That line again is the one Bunsen noticed when he burned hydrogen, and this dip here is from our star. Notice it's coming and going as our seeing changes. We're all familiar with the fact that we can stack images and eliminate noise. Well, I'm going to do that right here in the software. For videos, we can stack. I'm going to turn on stacking. Watch how quickly that feature stabilizes, becomes symmetrical. And now the video is still running, but now we've got a nice stable view. It's not as interesting to the crowd, but it, again, helps us process our data. So this could be a video. It could be a FITS image that you captured with your camera and whatever camera control software you're using today, and it can be set up. RSpec can automatically load those images as they hit your laptop. So that's really all I wanted to show you in the software. Let me come back here and share the screen, and that would be this screen. And here's a star party. You can see they really went all out with this projector. You probably wouldn't do this at a dark sky site with all that light, but they're looking at gas tubes here, and then they transition to stars. Here's a DSLR view with some stars. There's the gap. There's another gap on these spectra coming off those stars. Here's a star there with some lumps, right? So these are, they're emission lines. The gaps are absorption lines. Now, these are wider than the spectrum because we've saturated our camera, and we have a little bit of blooming. But let's look at an emission object. Now, I have a confession to make, and that is when Janet sent me this about 10 years ago, I couldn't remember what a Wolf-Rayet star was. You may be in the same boat. Many of us have read about Wolf-Rayet stars over the years. And this gets a little hot, so I hope you'll forgive me for taking it off. Things go in one ear and out the other. Wikipedia is our friend. That's a semi-ding moment, because these days, of course, the web makes things much easier than it was when a lot of us were learning this stuff 20 or 30 years ago. Learning just about how to use a telescope or any of that. Now we don't have to beg people at a club meeting to help us figure out what's not working. You just get onto a forum. Wolf-Rayet stars are late-stage stars. They're massive. They're shedding their outer shell. They're dissipating gas, intense stellar winds. They're probably headed to being a supernova. And here's what that emission spectrum looks like. So we've got these peaks here from those bright areas, and it's carbon, carbon, carbon. Why would we be seeing carbon glowing on this star if stars are all made up of hydrogen? Well, of course, stars burn through the elements sequentially. And part of that process involves carbon. In this late stage star, we're seeing some of that carbon. It's pretty amazing. So this is an emission object. Let's look at another familiar emission object, our ring nebula, and that's what its spectrum looks like. You can see there's just two colors there for hydrogen alpha and this oxygen. That Roman numeral 3 means it's ionized. It just means some electrons have been pulled out. Well, this is practically the only extended object that looks interesting in a grating like this. If we want to look at extended objects, then we need to spend a little bit more money and use a slit spectrometer. And you can see here, they're literally an order of magnitude or more expensive. And they're also much harder to use because now we're imaging through like a 20 micron slit. We have to find and track our target through. So they're a challenging proposition. And almost nobody, 1 in 100, tries starting with these because not only are they technically hard to use and expensive, but there's a lot of understanding that we gain easily when we're looking at a spectrum like this, because these just look at a tiny little spectrum rather than the whole broad spectrum. So here's again another emission object that we're familiar with, M42. So it's certainly an extended object. Look how nice and narrow these peaks are for that hydrogen alpha, and there's that Roman numeral 3 for ionized oxygen because an electron's been pulled off. So I'm going to stop sharing for a moment, and just because we have a minute here, just to ask, and if nobody cares to share, that's fine. I certainly won't call anybody. If somebody can share with us the first time, it's fun to hear, the first time you saw M42. Where were you? What did it look like? What was the telescope? What was your experience? Anybody want to share that? You can unmute yourself. And if not, that's okay. Anyone? Bueller? Anyone? Okay, well, in that case, you're going to get stuck with my story. And it's a simple story. And that is that I was in Denver in the early 90s. I wanted to see Shoemaker-Levy 9. I'd seen gorgeous pictures of stars and things in the sky. I wanted a telescope. I went to the Denver Astronomical Society first quarter star party in the city. I walked out from my car to the observing field. It's really fun. You might have had this experience in other areas when you can remember before you knew something. And this was one of those cases, because when I looked out on that observing field, I saw 4 or 5 things that to my uneducated eye looked like, those cannons that they shoot people out of at the circus? That's what I thought I was seeing. I'd never seen a daub before. How would I know any better? Anyway, I got in a queue. I queued up. Somebody much like all of you or me were running a Dob. They were looking at this great object, M42. I was really excited. I got up to the eyepiece and I was really disappointed. That was the story I was fishing for from one of you. And sometimes I get it, sometimes not. Some people say, oh yeah, it was a 24-inch Dob. I could see the green and I could see all these. And I'm thinking, that's not the story I wanted. So again, many of us have been disappointed that way, I'm sure. But I still, and I bet those who've been disappointed, still go back and look at M42 today. Why, if it's a disappointing object, would I do that? Well, of course, we observe in dark sky sites frequently. And also we have better telescopes. And also, of course, we've gotten better at using averted vision, right? Like I'm showing you here. You can actually, you don't need or you can use the more sensitive parts of your eye on the periphery. But really, the reason we go back, I would say, and this is a ding moment, and that is that now that we understand what we're seeing, and it's a birthplace of stars, a stellar nursery, and now it has more meaning to us. And the point is, and you've experienced this, the more we understand about what we're looking at, the deeper and more interesting the experience is. And that's something that spectroscopy has done for me. It really has deepened my appreciation of other activities, visual observing and imaging. So here at the top, we can see the specter of Uranus and Neptune. You can see those gaps there. There's a graph of that region. That's not a line, that's one of those bands. And we heard earlier how bands mean cool because bands are from complex molecules that don't get burned up. Uranus and Neptune, what would be cool on Uranus and Neptune? Well, what about the methane atmosphere? Same guy, Torsten Hansen, with a video and an 8-inch Newtonian, he shot and captured the atmosphere of these. It's just astonishing what's possible with such simple equipment. So in 1881, Henry Draper observed a comet, and the New York Times thought that was interesting enough to publish an article on it. Heck, if Hank can do it, so can we. So there on the bottom left, you can see the spectrum of a comet, and there on the right, you can see the intensity graph of the swan bands, these carbon lines. So this was captured by a guy in Northwest India, Vikrant Agnihotri. He's a nuclear power plant engineer, and in 2013, he was a newcomer. You can see he didn't use very complex equipment. Now I learned from him. He's a real expert, and what teacher doesn't enjoy learning from their student? And the reason I mention that is because I do a lot of mentoring and tutoring of amateurs as well as high school students. In addition to going in and showing spectra, in a sort of a open star party type environment for a school, you can actually, and in this way, you can get the cream of the crop. Ask any of the teachers there, do you have any students who might be interested in doing a science project or of spectra? And then you can take them on if you care to, as things open up again next year and the years to come, and actually mentor them. It's incredibly rewarding, and it often wins science fairs. So here's a more contemporary example of the sodium in NEO-WISE. You can see the tail there, the yellowish glow of the tail. This is done with an objective grating, which is you've got a grating right on the nose piece of your DSLR. Sometimes that's superior, even with a small aperture, superior to a telescope. So I love this. This guy, he C-clamped on a video camera to his mount. Now, I break everything. And this is a ding moment because the point here is that I mentioned earlier, you don't have to be a do-it-yourselfer. You pretty much, and that's what Robin Leadbeater did here, you just screw the grating right onto the nose piece of whatever imaging equipment you're using. And Robin Leadbeater, who designed the star analyzer, captured in a single video frame the spectrum of a meteor, one of the Perseids. So this is the meteor itself, and this over here is the spectrum, and that right there, that gap is that big dip. So he was able to identify some of the makeup of that meteor. This is a weird sort of sub-branch of spectroscopy, but whatever floats your boat. Some people love doing this. So we're not going to talk much about the sun tonight, except I'll point out that this yellow line was observed, as you can see, in 1868. They went back to Bunsen's records and they found nothing that glowed at that particular wavelength, about 5,800. They said, we don't know what that is. We don't have it here on Earth. So we know a physical property of it, this yellow glow when it's burnt. Let's just give it a name so we can talk about it. Greek for sun is helios, they named it helium. Now you fast forward about 40 years, some professionals in 2 different countries were burning some gas that they had created. And they looked at the spectrum to try and identify it, and they saw that yellow line. They were able to say, eureka. That stuff on the sun that we named helium, we've now found it here on Earth. I love this story because it really shows how effective science can be done at a distance with spectroscopy. So if you're into novae, you can see here, there's a dip here for iron, and this nova done with just a DSLR, but not this one. Just a quick review. Doppler shift is the sound change, for example, that when a car with its horn goes past you or you go past it, it goes, right? High as it's coming towards you, low as it's going away. So again, low as it's going away, higher as it's coming towards you. The same thing happens with light. So if we were looking at a spectrum and expecting this triplet to appear right here, and instead we found it over to the right, we'd know that object was moving away from us from redshift. And this is how we do a lot of science with spectra. If the lines were shifted over to the left, we'd know the object was moving towards us, or blue shift. Let's see an example of that. So there's lots of different types of supernovae. There's one particular type, and many of you may be familiar with this, called a type 1a. And it's when a binary system has 2 stars, and this larger star, some of its gas ends up on the smaller star. You pour gas on something small, what happens? You get an explosion. So here's a supernova in M101. Here's a photograph of another type 1a supernova, not this one that was closer to us. But you can see there's sort of a spherical shell look there, like, like an explosion is expanding. Well, David Strange captured this spectrum with just a 9-inch SCT and less than 15 minutes of stacked images. And that's what this spectrum looks like in my software. And the cool thing is that faint dimming we see there is really clear here. So, it's an overused expression to say we stand on the shoulders of giants. So, but the giants figured out some amazing stuff, including the fact that these ultra bright supernovae, there's different types. There's this binary pair one. There's also some that collapse because they run out of fuel, single star. They all have their own spectral signature. So now this won't be on the quiz later tonight, but I wanted to show you that a type 1a supernova has a really deep dip of sodium right at about 6,000. But notice that these other supernovae type, these core collapse types, well, for example, this type 2, it doesn't have any sodium, but it's got this huge red peak, and that's hydrogen. So these fingerprints allow professionals and amateurs to identify supernova type. And this is something that professionals would like us to do, to help them categorize supernova, because you only have a few weeks while this shell exists where you can actually detect this change in spectra and also the blue shift. So the problem is that most supernovae are really far away. They're not in our galaxy, so they're relatively dim. But there are opportunities, and as I said, this is one way that we can participate. I want to show you one other quick thing we did with this. David Strange and I measured that wavelength down on the x-axis, and we just noted it. Then we got online and we looked up, if you burnt beach sand, silicon, where would you see it in the lab? Where would it glow? And that's at 6355 angstroms. So the difference between those is due to some sort of Doppler shift. So look, I used the Doppler shift formula once in high school, maybe. I didn't know, I couldn't remember it, but Wikipedia is your friend, there it is. And when you plug the numbers in, you calculate the speed that shell is expanding. We're using the blue shift of that shell to see. That's incredible. First of all, it's fast, but it's also incredible we were able to do that on a backyard telescope. Now, we look in the backs of magazines and we see these gorgeous images of nebula. And I think one of the reasons I was disappointed with M42 that first night I went out is I was expecting to see something like that. But if you read the fine print on some of those magazines, you see that, it's like 25 hours of imaging time. I live in Seattle. I don't get that much imaging time over this whole summer sometimes, because it's cloudy here a lot. But the reason I want to mention this is every example I'm showing you tonight is done by somebody, a normal guy like the rest of us, or gal. And these are not the cream of the crop. These are the bread and butter that anybody can capture with relatively decent equipment, 4 inches, 5 inches, relatively dark skies. Many of them you can do in the city, as I mentioned earlier. So Adam Rees, you may recall that he and his team before the turn of the century were studying the cosmological expansion accelerating in the universe. And they used type 1a supernovae to do that as standard candles. Somehow I don't think they used this particular piece of equipment, but actually I threw it away today. I tried something last night in a talk. It didn't go so well. I'm going to try again. It's real quick. We use various ratios in science in observing. Signal to noise ratio, right? The ratio of the signal to noise. Well, I have a new one that I'd really like to be using. It's called bang for your buck. And if you look at the buck number for me versus Adam Rees, I've got him beat, right? $200 for this. How many millions are in his telescope? Bang, how do you measure? What's the quantitative measure of bang? Well, I didn't have to get a PhD and compete for funding and telescope time. I get a lot of bang. I can observe these things. Anyway, again, I don't know how to present this, but I like this bang for your buck formula. We don't normally think of it as an arithmetic like that, unless it's signal to noise ratio. What about the spectrum of a black hole? Well, of course, the black hole doesn't emit any light, but the accretion disk around it spiraling in, that gets very hot and emits light. David Strange down in Portland, Oregon, captured this of 3C273. I've never imaged it. There's a spectrum at the tip of those arrows. You can see 2 little dots. Let's zoom in on it. There's those 2 dots, and there's the spectrum. So this guy was in his mid-20s in the 1960s, and he was studying this. And he wanted to figure out what this object was. Why did it have all these emission lines? Usually stars have absorption lines. So he was really frustrated, and he did what a lot of scientists do. He said, let me start eliminating things that those lines can't be. And so the first thing to eliminate, let's prove they're not hydrogen, okay? So he brought up the reference lines for hydrogen. This is that image from my software I asked you to keep in your mind's eye. This is Vega, but the thing that I wanted to show you here are these reference lines. That's the Bomber series. And he went, well, they don't really line up with any of these peaks. So, I've proven that we're not looking at hydrogen here anyway. But they were. And he figured it out. Those lines were massively redshifted because this object was so far away. So using the Hubble constant, first of all, we were able to calculate the redshift close to the published value, but then he and we can calculate how far apart are we from that object. That's a funny way of saying it. How far away is that object? Well, I know one of the things I think all of us enjoy is the differences in distances and size and the enormity that we sometimes see in astronomy. Forgive me for sharing this one with you. This object is 2 billion light years away. And it's so bright, if we can see it here, intrinsically it's so bright at that distance, it must be 100 times brighter than all of the stars combined in the Milky Way. That's pretty astonishing. One final light comparison, and that is, if it was a star, and we know how enormously far away the stars are, it would be as bright as the sun to our eyes here on Earth. That just blows my mind. So the cool thing is that we're able to use simple equipment to do that. And to me, what it really is amazing is that this light that has come such a long way over such an enormous, immense eons of time, 2 billion light years, still has the data in it that we can pluck out with such simple equipment. And it's like the light didn't age. These peaks didn't fade over time. Now, humans aren't quite as fortunate. This is Martin Schmidt a few years ago. Now, listen, I've been justly accused of, throwing rocks in a glass house. He's got a full head of hair and I don't. I'm envious of the guy. Just give me that. So 2 more examples and we'll finish up. So far, we've been looking at features like these in Vega, mostly. Suppose we wanted to zoom in on this feature. And we can't just use our mouse wheel and zoom in, right? Would that we could. But, that we've all experienced this. We're looking at the moon through our telescope early on in our telescope careers. We go, let me get a higher magnification eyepiece so I can really see more detail. We keep doing that until we start noticing, it's bigger, but I can't see any more detail. That empty magnification is what happens if you use your mouse roller wheel on this data. So to drill down into this, you need to use one of those expensive slit spectrometers. I want to show you two final examples quickly about what we can see with a higher end device. There is that hydrogen alpha feature on a slit spectrometer. It's very deep and there's other features that we can see. But if we compare it to the moon, like scientists often do, comparing two objects, one known, one unknown, the moon isn't moving towards or away from us, but notice Vega isn't in the same position. There's some Doppler shift going on here. And we can just measure that distance here, the difference in wavelength, and we can calculate the radial velocity of Vega. It's amazing with a slit spectrometer. One final example. I have a visual aid here I want to use. So this is a spinning star. It's rotating, in this case, very, very fast if I don't drop it and break my keyboard. This, in fact, here I've got an example here. There's our Vega again, but this is what I wanted to show you. One edge, this edge is coming towards you, and so that light is blue shifted. The other edge is moving away from you and it's red shifted. John, this you may have forgotten a lot. Maybe you saw a lot of what I did tonight you've seen before. This is a new graphic, which I think really helps. So what would a really rapidly spinning star spectrum look like? Well, some of the light that's here wouldn't be here, it would be over here. And some of the light that's here wouldn't be here, it would be shifted, blue shifted and red shifted. Let's look at what that looks like. There's Altair in blue. Notice how broadened it is. The giants really were clever men and women that they've been able to figure out so many things about the stars with such just a rainbow from the star. So how do you get started? Real briefly, you need a grating we've talked about. You need almost any camera, color, mono, whatever. You need some software to process the data. That's my software, RSpec. There, it's a site down there. R stands for real time, because you can look at Spectral real time and video, and even still images can be popped up real time. This is the software I tried years ago. I had so much trouble with. I'm friends with both the authors of that. In fact, I gave a talk to the AVSO. I was in a big webinar about 10 days ago, and they were there. I've met them in person at a star party. Great people. The software is still rough and very powerful, but a very steep learning curve. You may need some spacers, and that's because this distance, although not critical, we don't want the grating too close or too far away, because we don't want the spectrum spreading out too little or too much. There's a little calculator on our site where you fill in your telescope specs and your camera specs, and we show these green flags if everything's okay. Frequently, people just send me their telescope specs, and I figure it out for them and make a little screen video and explain what they need. We have a couple different types of gratings and spacers and things. There's lots of books out there. This Spectral Atlas is really a pretty cool book. I talk about it here on the site. I just want to show you a sample page from it. You can see it's showing you, well, if you're seeing two big peaks on this ciphered galaxy you're observing, and you can do this with just a webcam, then you're seeing ciphered, you're seeing what you're expected, and those are oxygen. There's some nitrogen, but I'm a knuckle dragging programmer. I don't know the significance of any of this. The cool thing about this book is not only does it have those images and helpful keys like you're seeing there, but there's also a lot of text aimed at us, not astrophysicists, but amateurs. And it's a great book. Also, we've got a great forum with lots of experts who love sharing what they know. It's a great place to ask questions of. About 4 years ago, I gave a talk to the AVSO. It was a live conference in LA, California. It was a hands-on workshop. Everybody had their laptops and some sample data I sent them. The software is free for 30 days, so they were all running it. They recorded that and it's on YouTube. So tomorrow morning, let's see, what day of the week is this? That's also a problem this year. Thursday morning, if you have some free time, you can download the software data, the sample data, and then watch that YouTube video and go through, even if you're an armchair astronomer and never plan to do this again. When you were done, you would have spectra in your bones. I guess there's bones here. I'm trying to, hit my collarbone here or something. Anyway, there's opportunities to do pro-am collaboration. This is a BE star. These are all amateurs here. This is a cool star. And this is, again, all I know about BE stars. I read about them now and then, but I just haven't dug in. They're type B stars. They're hot stars, but they have a circumstellar disk that glows, so they have emission lines. So we've come a long way in the last, 50, 55 minutes. I went a little over, my apologies. We've also come a long way in the last 300 years or so, starting with Newton. I'd like to thank you all for smiling at some of my jokes and for inviting me tonight. I appreciate all of you who do outreach. I think that's one of the more important things we can do these days. The world will get normal again and we'll be able to do it again in the coming year, we hope. Again, it's one way, of course, that we pay it forward as well as backward for the opportunities that we all had and were able to take advantage of. I'm always available for questions, not only now, but there's a contact form on the site. You can always send me email. I love the field. I love helping newcomers get started because it's really exciting to be helpful and see somebody's excitement when they capture their first spectra. So I'm going to stop screen sharing here. If people have any questions, I'm sorry if it felt like you were drinking from a fire hose. The presentation used to be longer, and I hate to cut any of those out because those samples are so fun. So just feel free to unmute yourself. Chris, you look like you've unmuted yourself. You have something to say?
I do actually, Tom. Thank you for that. That was actually very, very entertaining and a lot of fun. Very interesting. I do have one question. You had near the beginning, you had an example where you took the first spectrum and you made a graph out of it, and then you went back and using that graph, you chose to look at the hydrogen spectrum.
Yes.
Now it looked to me like you knew that what you were looking at was hydrogen.
Right.
For somebody like me that would take that initial graph,
Right.
not having any idea what I'm looking at, does that work in reverse? Can I take a graph and say, okay, what am I looking at? Will it tell me what I'm looking at?
The software won't tell you. And that's a really good question. First of all, well asked. I appreciate your terminology, and you've really identified something that's good for us to talk about a little. And that is, it is hard just looking at something like this to know what it is you're looking at. Most of what we do as amateurs is we go after targets that we already know. We know that a type M star is going to have these wide bands over here. So we more or less know the answer.
Right.
But once we get comfortable doing that, then we're in a position to look at new things and go, that sort of looks like that banded whatever that I saw before. So it can be a challenge to identify what's what here. I mean, one way to do it would be to go through one at a time and see which lines match the closest. But
Okay.
that's not very effective, and it's also rather time consuming. Just to show you over here, titanium oxide, look where we would see some really deep bands if we were looking at titanium oxide.
Right.
So your question's a good one. My site has a samples page with a lot of the samples I showed you here tonight, as well as some additional samples. Typically what people do when they get started is they always start on a type A star like Vega, which is what this is, because it has such strong hydrogen alpha lines. So it's the easiest to get set up and to learn focusing and exposure levels and stuff like that. And then some people experiment and go, well, let me look at a cool star and see some of those bands. And then they just branch out. So there are lots of opportunities for us to explore work that's been done. And then as we get better, begin to look for things that might be new. One of the things that at the AVSO conference last 2 weekends ago that I found particularly interesting was a professional, a guy named Steve Shore, an American who lives in Italy. Just a brilliant guy. And he was talking about pretty much the same thing, which maybe we've heard over the years, and it still holds. And that is, even more so now, we can't compete with the professionals, especially with the new surveys that are going on and the aperture that they've got. But where we can compete, he pointed out, is, well, first of all, there's not as much spectroscopy getting done by the professionals with airborne assets. We've got Gaia and other things that are mostly looking at photometry. But we can do what's called, I love the expression, high cadence observing, meaning we can look at the same thing every night. And we can have amateurs all over the world looking at something for a period of 24 hours straight. The professionals can't do that. And so the advantage is that we can fill in that gap. The other thing these professionals can't do is they can't look at really bright objects because their telescopes are too sensitive, which is always amusing to me.
Huh.
You know, it's sort of like, well, turnaround's fair play to be able to say, yeah, too bad, tough guy and tough gal. You've got too much aperture, you know, so bad on you. I have a quick video I thought I'd show you here of, it's actually on my site. So let me just bring it up and give me a second here to share that screen. And you can't see that yet, but you will be able to in just a moment.
And no, you didn't run late while you're bringing it up. We
Okay.
waited till people started. We introduced you,
Oh, good.
and you were right on time. So you're not
Great. Well,
running yet.
Here's Chrome. I don't have anything here I don't want you to see. Not that I ever do. But yeah, I don't think so. Let me quickly look. Hey, I'm making sourdough bread during the quarantine. That's news, right? Who isn't? So, but what I wanted to show you on my site was this sample projects page, because I wanted to show you Lyra. So I'm going to show you, it's like a 10-second video of this spectrum. It was done with just a 4-inch refractor in less than 2 hours by this guy Solaccia in Italy. And what you're going to see is, again, this is the hot region, blue, and this is the red region. And we can talk about that later if it comes up. But you're going to see the whole shape of this curve change and some new features appear in the spectrum. So watch as this end gets hotter, those hydrogen features, deep dips appear. That's the whole video. It's just repeating itself now. And the shape of the curve, it's getting steeper because the star is getting more light in this blue region. So this is the kind of thing that we can do. And truth be told, this wasn't done in my software. I don't have this animation capability. But this is the kind of observing that we can do. So that was a good question, and I appreciate it, Chris. Other questions people may have or follow-ups?
I have one for you, Tom. When you're looking at some of the spectra, and you can certainly point to a dip and see what angstrom level it's showing, do you have a chart that also lists the elements by angstrom instead of elements by name?
That's a really good question. I don't. I know there's software out there that does it, and I mean,
get it done before the update of my license expires, will you please?
There we go. It's really like looking for a needle in a haystack when we look at the spectra. I mean, for example, this is a high resolution spectrum of a comet. But there's a lot of peaks here. Again, a lot of carbon, some oxygen. So there are lots there. I showed you all that. There, I showed you that. So this is the samples page on my site. So you can come back here and look at some of the things, some of the examples, and look, there is, what happened to that one? It's a broken page. Anyway, good question, John. Thanks for, I don't have that now because most of the time we know what we're looking for. And that's where this book is so helpful. It goes through every star type.
I'm glad you brought that up. Could you please put up those books again that were in your slideshow and leave them there for longer than 3 seconds?
I will. And even better yet, I'll point out on this links page, if you scroll down to the book section, here's perfect. That book. That's the one I've been talking about. Again, you know, this is almost TMI, but won't embarrass anybody. So I got a new prescription from my doctor last week. Actually yesterday. And he didn't tell me when I went to pick it up. It's like, this is freaking expensive, you know? He didn't want to be the messenger of the bad news. It's a blood thinner. Some of you may know why and when people take those things. I'm healthy, but I need a blood thinner. So that's what I'm doing here with this book. This book, if you go out to Amazon and look at it, it's like $80. But I'm not going to tell other clubs that. This is like exclusive for you all. I don't want to be responsible. Let you guys figure that out when you go out there. Now, here's another, it's not a secret, but another thing that can be somewhat amusing. These links here, if you go to Amazon with, and I actually say it at the bottom of the page because it's required by the FTC, I make a tiny bit of money. And I think I actually went out there today. I don't usually go out because it's so uninteresting to me. I make about $35 a year when people click on these books. I mean, I was like thinking, oh man, I'm going to just rake in money. But the cool thing is that most of us didn't know, and I didn't know until I set up this affiliate thing with Amazon, is I make money on anything you buy during that visit. And so I've made like 4 cents on somebody buying a My Little Pony doll, a pink.
Oh,
It's always funny to look at that and look at those reports. But like I said, so this is a really fun book. You'll see the review. Actually, I was reading the reviews on Amazon today. The review, one of the people says it's too advanced, but then everybody else says this is a good book. There's other books if you just want to read a little more about the science. These are more or less in priority order. This Keith Robertson, these are all part of the Patrick Moore series, so they're relatively small paperbacks. Zero Math, in fact, I spoke to Steve Tonkin's club in the UK a couple weeks ago. Any book with this is as part of their title is always suspect to me. You know, Astrophysics is easy. That's not the book I want to be carrying on the bus or the subway. You know, I'll get beat up, you know, I'm this emaciated kid, you know, somebody will come on, knock the book out of my hands. Anyway, there are lots of interesting books for you to look at. And also there's other information on the site that I think you'll find interesting and worth cruising through. Other questions people may have? Well, listen, it's getting close to dinner time here. Oh, so Vince, that's a different background than you had. You're no longer in your man cave, are you? You're now out freaking side. You're muted. I can't hear you. We can't hear you.
You have to unmute yourself by bringing your cursor. There you go.
I put up a screen. The reason that it's a start is I don't want you to see the mess behind me.
Oh.
I have actually thought of that, and there's a background that I was thinking about using, but I just have decided that maybe it wasn't the most appropriate. There's nothing wrong with it, but you can see what it is there. I'm just in an urban setting of some sort. If you don't know what that is, that's okay too. Just outside in some junkyard. Anyway, let me turn that off if I may. Listen, guys, thanks again. And thanks for doing the outreach. John, thanks for setting this up. I hope that there was something new in this. John, I mean, really, I've spoken now to more than 300 clubs. So I may have this dubious record of having spoken literally to more amateur astronomers, between 5,000 and 10,000 over the last 7 or 8 years. John, you probably have the record, and you know, my hat's off to you of having heard this talk more often than others. The interesting thing about these talks is, you know, you never want to go see a stand-up comedian. Not that I'm saying that's only what I did tonight, but you never want to go see a stand-up comic 2 nights in a row, because all those offhand, spontaneous comments you hear again, and you go, wait a second, that sounded spontaneous last night. He said the same exact thing.
Yeah.
The things I did tell you tonight, this is new to me, and some of the other things.
I want to bring it home to my husband.
Ron, thanks again for setting this up and for all you do to keep the club engaged in presentations like this. I'll leave now. You all can talk about me behind my back. Thanks again so much.
All right, Tom.
Thanks for joining us, Tom.
My pleasure.
Thank you very much, Tom. Thank you.
You're welcome.
Thank
Thank you all. Good night. Your thanks mean a lot to me. I appreciate it.
Good night.